this actually makes sense in context of, you remember how an X-ray, you took a sample, you laid it out flat on a surface, and then you changed the angle you're shooting the X-rays in, and depending on what angle, you got constructive, destructive interference because it bounced off the atoms, right? Okay. You're essentially using that same phenomenon here. Okay. So depending on the angle that the light comes in on, it's depending on what type of light you have, it's going to exhibit either constructive or destructive interference. So if you match up this incident angle and the diffraction angle right here, you'll have beams that the light is either coherent, in which case it's constructive interference. And so you'll end up selecting for that specific frequency of that light, where its wavelength is matching up with this diffraction angle here. Okay? Or it'll be destructive interference, and that's what you're seeing with the green here. See that? It's going to bounce off at a slightly different angle. Okay? And see how they don't, they wouldn't match up if they were to do this angle here. Is that making a bit more sense? Okay. And so what you're seeing is, have you guys seen the bottom of a CD? That's what you're seeing. That's actually diffraction. So that's grating, just like this is. It's just burned into like a plastic disc. And, it's actually not bad grating considering what it is and how fast it's made. You could actually make a spectrometer from them. I mean, that's what a disc reader is. It's a spectrometer reading off the diffractions. And so this right here is actually what the formula is for this. And so right here, this is the incident light right here. And then this right there is going to be the angle that it should diffract off if it was perpendicular to the grating right here. Okay. And then the distance is going to be the distance between the grating, the distance of the gratings. Okay. And so this then is going to be the angle here. That would be right there. Can you see that? So it's this angle. That's the difference between the emerging light versus your perpendicular line. This one is the incident light versus the perpendicular line. And then those are going to be what you're taking the sines of in here. You add the sines of those together, and then you multiply them by the distance. If that is a multiple of the wavelength, that's the wavelength they'll select for. Okay. Now, this number, this is going to be a constant because once you've made your grating, it's going to be D, right? You're going to have a distance between the grating. It's not easy to change those. Okay. This right here is the terms that can actually change. Okay. Specifically, the one you're typically going to change is going to be the incident angle right here, right? Which is this theta here. Okay. And so what you do is you take the grating and then you move it. So this is the incident light coming on the grating. And then you move the grating to change that angle. See that? Okay. If you move that grating to change the angle, then you're going to have a different theta. This is going to give you a different multiple of your wavelength. Did that make sense so far? Yeah? Okay. Okay. And so now, if you're ever looking at this again, this is going to be your incident light. You have your emerging light right here, which is your diffracted light. And then the facet normal is going to be where it would be directly off of the facet. So bouncing exactly backwards off of that facet, where you're lined up directly with the facet, or a 90-degree angle of the facet. This is referred to as the Blaze angle, by the way. It's the difference between the angle of the grating versus the angle of the just flat surface that you would have had it. Okay? literally blaze, as in they used to burn this out. Yeah. And so, like, you would actually create these by typically burning process off these. You can do it several different ways, but most likely, have you ever heard of burning a DVD? That's what you're doing. And so you're burning a DVD plays. Okay, now, so what are we talking about? Well, we're actually, again, talking about CDs, compact discs, or DVDs. So this is actually a CD. Again, here we have our incident beam. It is a grating, of course. And so our incident beam here has a multiple N1 of its wavelength, and that's that beam coming off here. And then we have a multiple N2 of that wavelength, which is that one. And then this one would actually be an N-1 multiple. And so we see beams coming off in those three directions from this disk. Okay? And that's because that's selecting for our red light, right? That we have a grating that's a multiple of the wavelength. Okay? We see almost no wavelength off of the other angles because those would be destructive interference. Okay? Now, if we start putting in different frequencies, what we can actually get is, see the green versus the red here now? Okay. So the green laser is going to give its own -1, 1, and 2. Okay. We won't get the other ones because there's too much space here. Does that make sense? Like, the incident isn't great enough to allow us more ends. But if we changed our incident, we could change the ends that come off. Like, if we were to come in this way, we could get the N1, 2, and probably 3 and 4 as well. Looks like. Now, whenever you're looking at like a compact disc player, interestingly enough, they typically used different light sources, different lasers. And so there actually is different discs, especially in like the early days. So you would have discs that were active in the yellow, discs that were active in the green, discs that were active in the red. Later on, they were able to fit more data by using multiple lasers. Okay. And so, funny enough, I guess the yellow lasers used to have issues, and they'd be the first ones that would always go out. And so ones that depended on the yellow frequencies to read the data would stop working. And your disc player would still work with like 90% of discs because they were green and red and didn't depend on the yellow. But the yellow ones would no longer work. So that's kind of interesting, right? Weird. This is why it happens. Because each of these would have its own instance, right? Yeah. So the resolution of these, the minimum wavelength difference, delta wavelength between two peaks, this can be, of course, distinguished from each other. The resolving power is going to be that wavelength divided by delta wavelength. Again, the delta wavelength is going to be resolution here. And then this is going to be your wavelength, resolving power being what can you resolve in terms of detecting if it absorbs or does not absorb at that wavelength. Okay. The resolution is going to be better the smaller the number, and the resolving power is going to be better when you have a larger number. So if you have a resolution that's a very small number, this is going to give you a very large resolving power, right? Because you're going to divide by a very small number. Okay. This is the resolving power of a grating right here. It's going to be the resolving power right here equals N times the large N, which is going to be the numbers of grooves in that grating that are going to be illuminated. The more grooves you can illuminate, the more resolving power you're going to get. Okay, so let's talk about dispersion. This is going to be the ability to separate wavelengths by differing delta wavelength, or remember the resolution. And the difference in the angle, which is the delta radians and radians right here. And again, that's going to be this one right here. Note that because of geometry, these angles are the ones we typically talk about. But they have a second set of angles right here, right? So if you were to look at the perpendicular here, so the surface right here, you can actually go reverse from the surface to the incident light, and you'll get the same set of angles. So, yeah, you can also detect them from there. Okay. Do you guys have any questions about any of this so far? Okay. Do you want more of this information? Yeah. Okay. Okay. So this is what a typical instrument would look like for grading. Note that not all instruments use grading anymore, but it's still quite common. It's fairly low price because we've gotten very, very good at it with basically the same sort of methodologies used for like making very small structures on a discs or actually they used a really cool version of this recently. Microsoft did. They made these storage things that can store information for 100,000 years by carving it into glass and then seeing how it diffracts off the glass. So, kind of a cool thing. So this right here, light source, slit, we get it into a nice little narrow beam. Then it's going to spread out as we go away. This is a culminating mirror. It's going to get it so it's parallel. It's important that you put your light in parallel because if the light is not parallel, when you're putting it in to the grating, then the grating is no longer going to select for exact frequencies and wavelengths. And that's what you're seeing on a disc. It kind of selects in like a little area, right, for the exact wavelength. But you see that like blooms off on the sides really fast, doesn't it? If you ever look at the back of a CD or disc. By the way, CDs did not typically use blue. If you ever heard of a Blu-ray, that's like one of the innovations of a Blu-ray is because that has a smaller wavelength. You could fit more data on it. And larger wavelengths, you can fit less data because you can't resolve them as well, right? Which is what we're actually looking at right here. So, why couldn't you do a Blu-ray at first? Why didn't we start with blue? That was part of it. The LEDs and light sources for a blue LED didn't exist for a long time, so that was a large part of that. Okay. The other part is you also had to have a smaller gratings. Yeah. So the discs themselves couldn't. We used the exact same burners and DVDs. They had to be slightly different. Not that different, but you had to have a more precise grading. Some more gratings per surface area. Smaller distance between them. Okay, so this right here is going to be the grating and see how it has the incident angle. Okay, and notice that we're going to be selecting for one specific frequency of light. Let's call that green since it's colored green, right? And all the other frequencies of light are going to bounce off at slightly different angles, aren't they? So what we do is you don't normally have to you don't directly usually calculate this per se. It doesn't necessarily have to be a perfect calculation prediction for what exact angle you're using here. Usually what you do is you experimentally determine what angle gives what frequency of light. Alongside a little bit of a calculation so you have an idea. And so this facing, where it's giving the light, what you'll see is that only the wavelength that corresponds to that n multiple of the wavelength for the grating is going to hit this focusing mirror at the correct angle to actually focus and pass through the slit. The rest of them are going to hit the sidewalls here. In case you're wondering, yes, that does actually warm and heat this up. Okay? So it does heat up your exit slit. You'll select for a very narrow range of wavelengths, and that's what you actually get for the wavelength that you detect at the detector here. Is that making sense so far? Yeah. Okay. Typically, these mirrors will come as sets, by the way, with that grading. It is very important that they are properly calibrated together because the relative efficiency in the grading is this formula right here. And so it's going to be the E for that wavelength to the N here. That's going to be the grading one. That's going to be the irradiance at that particular wavelength of the diffraction of interest. The order of interest is N right here. The mirror is going to be the irradiance at the same wavelength that will be reflected by mirror with the same coding and grading. And so that would then be divided by this one. Notice it does not have the order of interest right here. And you can very well get this to be orders of magnitude less frequency coming out than you would need to actually get a spectra that looks decently. So this can actually take quite a bit of work. This used to take tremendous amounts of work, and actually is how MIT generated a lot of its science budget back in the day. So they're one of the few labs that could do this well enough to make instruments. So the efficiency is going to be partially controlled by the blaze angle, which the grooves are cut. And again, that's the blaze angle right here. See how it's the angle of the groove versus the surface. Okay. So to optimize diffraction for a certain wavelength, your blaze angle will be chosen to satisfy these conditions right here. And so what you'd see is that you want the alpha to be approximately equal to the beta. That is the angle to the facet normal to be approximately equal to the diffraction angle. So incident versus facet normal, approximately equal to diffraction. Okay. They typically will not be perfectly equal. You can actually see that from this one, that they're not quite equal, are they? But you want them to be pretty proportional, equal. Now, what you'll notice is that when you have a grading, if you looked at here, again, it's the incident and diffraction. These numbers change depending on what your wavelength is, right? And so gratings really only kind of work well for one set of wavelengths, okay? So they're going to have limited sets of wavelengths that they can work well for, right? And so what you'll see is that gratings can be designed for a limited range of wavelengths, one of which is going to be really good, and then it's going to tail off from there, okay? Now, there actually it's not a perfect like drop off, like not all of them are Gaussian, they're never Gaussian distributions. And so you're going to see that this right here is very obviously, and you can actually get increases later on in the wavelengths because they happen to match up to an N wavelength, right? And so, for example, this 1000 nanometer blaze right here, see how it has like frequencies that it gets better at again? Okay. So typically what you see is you either have an instrument that only has a very limited frequency range or wavelength range that it can work on, or you have multiple gratings. And then you'd have a mirror system where you can put it through one beam, put it through a different beam for the grating, and exchange the gratings as you go along. Depends on what you're doing. Those would obviously be more expensive systems, which is why you guys haven't seen prices at all, but you'll notice that we have like different UV visible instruments, and they're like very obviously different in terms of price. The quality of the instrument really changes and drops off. And that's because as you get a wider frequency range or wavelength range that you can use on those instruments, you have to have different types of gratings, and oftentimes you may have to have several gratings, in which case the instrument has to get much bigger, right? And so that's actually what you're kind of seeing there, is they're having gratings that are optimized around certain frequency ranges. or wavelength ranges. These are the blazes. This is the wavelengths that you would see for those. And you can see like this is really great as long as you're doing something in like the 200 something nanometer range, right? Not great if you're up here. It falls off pretty fast. 1000's excellent as long as you don't ever have to do anything past 600, right? If you go lower than 600, you're going to be in trouble. Okay? Yeah. The blaze nanometers typically are about where the peak is here. Okay, so what can we do for these? Now, in terms of this exit slit here, the wider band, if we increase the size of this exit slit, what is that going to do to us? Yep. So we're going to have a wider range of wavelengths that can go through, okay? Now keep in mind, like, there's fractions for wavelengths. So it's not like you can get it to exactly one wavelength for basically almost any instrument. Lasers do a better job of that usually anyways, but yeah. But the wider this slit right here, the more range of a wavelength you're going to get. And so you're going to affect your resolution, aren't you? Now we typically measure that slit in terms of the bandwidth of radiation selected by the slit. So instead of saying that we have like a 0.3 millimeter wide slit, we would go the bandwidth. And so that would be the difference between the highest and lowest wavelengths that we can select for. In this case, it'd be 1 nanometer. And so we have 1 nanometer of wavelengths we can select for. Okay, we'd be plus or minus 0.5 nanometers. Now, why would you ever not just use the narrowest slit you can possibly get? Well, if you do a very narrow slit, you're going to see very little light passing through, aren't you? And so you typically can't do too narrow of a slit. If you do too narrow of a slit, what you're going to get is your response here is going to go down significantly. So you're going to get less and less intensity. You'll get a noisier backgrounds as you cause that slit to be more and more narrow. And so while it does increase your resolution, it also is going to decrease your signal to noise ratio. Okay. And so this is what that looks like in terms of resolution. This is what that looks like in terms of absorbance. And so see, as we go down, when we have a pretty wide slit, we have lots of light coming through. When we have a more narrow slit, we're going to have a lot less light. And so there is a compromise to this. Typically, you're going to use a monochromator bandwidth that's 1/5 as wide as the absorption peak. It's going to give you the small distortion of your peak shape while still giving you sort of your maximum intensity that you would see for that. And that's sort of what you're seeing here. Like, for example, realistically speaking, is this much better of a spectra than this one? Do we really get any more information from that? Not really, right? Like, we still had the positions here versus this one. Yeah, we came up with basically the same positions, didn't we? Okay. And so if your background noise is very high in this one, going to this one is a very valid trade-off, isn't it? Do you guys have anything on this that you're having any issues with? Okay, you already did that. So when you calibrate an instrument, you always want to take a standard. One of the common standards, for example, is this chromate here, potassium chromate, for UV absorbances. They're ones that you know where the bands should be very well. They have very high accuracy, and you know what the relative absorbances should typically be. And so then you can scan those in your instrument, you compare them to a database, and then you can see if your instrument is reading within spec. Okay. Filters. Now, in terms of filters, what you'll see is that most sources are going to have stray light that will come along with it. And so you want to get rid of some of that stray light. And so a monochromator is going to be set to first order light at wavelength, a specific wavelength. It will pass second order stray light through, and that is going to be at wavelength of 1/2 typically. So 1/2 that wavelength. It'll also pass third order stray light, that is wavelength divided by 3. And fourth order would be divided by 4, etc. Okay. Now, what we typically do is we typically have some sort of filter. And when we talked about those monochromators at the beginning, you may have noticed that there was a filter process at that beginning portion. And we had talked about monochromator filters a little bit. This is going to be in front of the monochromator entrance slit. And so you're going to, like right here is a holographic filter. And it's going to very narrowly select for that specific set of wavelengths. Okay. Now, this would be what it would look like in terms of this wavelengths coming out of this instrument right here. See how it has a major drop off here and here? Okay, that's because we're filtering that. This is what a dielectric filter looks like, by the way. We can take out a portion of it instead. So the simplest filter is actually just going to be like colored glass. And then you can use different lenses of colored glass. Have you guys ever seen the old like bands performing? They have like lights there, and then they change out like lenses above it, and it gives the blue, green, red. Yeah, very similar to that. Okay, that's the simplest form of filter. You can use more fine control filters, interference filters. You can also use holographic filters. These are going to be specifically used to pass regions of interest through or reflect off other regions. Let's see. This is a detector. So this is one of the like older style detectors, but they still work quite well. So again, you have your monochromator. It's going through in the chopper, and it's going through your reference and sample cuvettes. You're going to hit your detector, and then your electronics is going to boost that signal so you can and process the signal so that you can then display your, hey, I got this amount of light, right, at this specific frequency. So what's going to happen is we need a detector that's going to transform photons that are being detected, right, into electric signal. Okay. And so one of the simpler ways of doing that, well, simpler is kind of a misnomer. One of the earlier ways of doing that, and still in pretty wide use actually, but not as wide use as it used to be, is going to be a phototube. What this does is it emits electrons from photosensitive negatively charged surface when it's struck by visible light or UV radiation. The electrons will flow to a positively charged collector, which is basically this arrow right here would represent that. And so that current that comes off of that is going to be directly proportional to the radiation intensity. Now, when we're talking about this photodetector, that material is going to dictate the proportion that's going to come off in terms of the electrical flow, that current, versus the wavelength of the light that's detecting. Okay? And so it's going to have these major things of what photodetector is going to work for what region. This is why you typically don't see an instrument that works with like UV, vis, infrared, near infrared, all of those at the same time. you can see, portions of that. You can get like a visible light near infrared instrument because they're pretty close in terms of wavelength. You can get a UV vis instrument, again, because they're pretty close in wavelength, okay? But you don't see a UV infrared instrument because they're not close in terms of wavelength, and so the detectors typically are not going to work okay. Now, there is a way to make that work, but it's not worth the price for the results you would get. Okay. Now, there's the spectral range of interest, of course. See how each of these different detectors gives you a specific coverage for those the spectral ranges. Have you seen the infrared backgrounds yet? No? Okay. We'll do that during lab. Yeah. I need to actually work on the infrared anyway, so we'll do that during lab, and I'll show you what the background looks like. You'll recognize this because the background actually is a reflection of this. Okay. So the other part is the light intensity. If it gets too intense, or if it's not intense enough, it's not going to detect anymore, right? So for example, if we go over the relative intensity of 1, if we get too intense, it's just going to cut off, right? Your detector can't detect that anymore. Same thing that happens when your phone, if you try like use your phone to do a solar eclipse, just shows a big blurry blob of light. It's overwhelming the top end of your detection, right? Similar thing happens on the bottom end of this. If you are under the detection limits, then you're going to see essentially no signal. Okay, it's going to essentially just be whatever your noise is for the detector. So a single wavelength or point in space is going to be measured, or a full spectrum or image is measured. So some of these you can measure essentially like a very narrow range of wavelength, and so it's essentially like a single wavelength that you can measure. Other ones you can actually make them like a little bit more like a camera. And so you can actually, instead of having just is it detecting light or not, you can actually tell where it's detecting light. Okay. And so then it's going to be like a range of space, right? And so you can measure different parts of that space. Okay. So you can get like full images, or you can just get one point in space, depending on what you're looking at. Or you could get a single wavelength, or like a spectrum of wavelengths from one detector, and that it can actually differentiate those different wavelengths. Okay. Now, modern phones and modern optics oftentimes is a combination of these things. Like we'll have detectors that absorb this, then another detector behind it, then another one behind that, and we'll kind of do that. Or we'll diffract them off to different detectors in each pass. There's a lot of stuff that can go on now. We can also, because we have very, very small optics we can now make with the, you remember we were talking about semiconductors and inorganic chemistry? So you can lay down very fine coatings on these semiconductors, right? They're really, really tiny areas. And so what you can make is you can make semiconductors that are actually photodetectors, basically reverse LEDs. Okay? And so that's what's basically used in your phones these days. You guys ever seen it without the optics portion? The actual like photodetector portion? If you ever got a good, like really nice digital camera, you can switch lenses in. You'll see it. It basically looks like a little computer chip behind there. Because that's what it is. It's a combination of detectors. They're laid out in a computer chip, essentially. Okay. This is a photomultiplier tube, PMT. These are still very much in use, but not as most commercial instruments are no longer using theirs. Most commercial instruments are going to use something you can lay down that's like a solid of some sort. Because these are actually quite fragile. They're very sensitive detectors, though, and they can measure the irradiation of light in very, very tiny quantities. And so, what's going to happen here is you have your incident radiation that's going to come in, and you'll have typically some sort of gas, but it doesn't have to necessarily be a gas. What's going to happen then is a light is then going to strike a photoemissive cathode, and it strikes that photoemissive cathode, and you're going to get a multiplication of the light. And so it sends out 2 or more photons for every photon that strikes. And then you actually typically build this so that it will diffract off, where it hits a series of these photoemissive that emits more and more and more each time. And then finally, it goes to the final portion where the anode, which is going to detect that flow of electrons that are going to be caused by this emission. Okay. And so what you end up getting is this takes a little bit of time, and so it's not quite as sensitive. It's not usually going to give you like that time response that you would expect from the other methods we've talked about. But it does give you this huge amplification, right? Because usually you're doubling every step of the way along here. And so you're doubling this, 1, 2, 3, 4, 5, 6, 7, 8, 9 times in this one photo detector, right? And so you can detect extremely small amounts of light. This is the sort of detector you use to detect like really far off spatial objects or very, very faint signals that would come out. Okay. These do actually get overwhelmed and reset. In case you're wondering, these same sort of detectors actually is very similar to how a Geiger counter used to work, the old ones, where it was a tube of gas. That was just a gas, and every time it got struck, it itself struck other gases, and then they amplified the signal out. And so that works quite similarly. And you get basically bursts of signal. By the way, that's why the Geiger counters used to go kick, 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 like that, make the clicking sounds. Because it would get overwhelmed and then have to reset, and then get overwhelmed, then have to reset. The faster it's doing that, the more radiation that's coming in and causing that. Now, again, this is very, very, very low intensity radiation you're detecting here. This is what's needed to actually boost that into electrical signals that you can actually detect. 10 to the 6 electrons may reach the anode for every photon that's striking the cathode. In a more traditional detector, it would be more like a 1-to-1 ratio, and you may do gain, where you're doing like 4 times. Okay? And you'd have a fairly low amount of amplification. Now, note that when you do these methods where you're multiplying these photons, one of the reasons, see how it has this fairly complicated shaping of reflections where it does these diffractions here? This is to try to cut down on noise. So every time that you multiply like this, you can multiply the noise as well, right? And so this is very specifically, very carefully designed to cut down on that and give you the least possible multiplication of noise. Again, the cathode will emit electrons when struck by the light. You're going to have a series of diodes. Those are the same diodes as you've heard of in like electrical things. These are the plates. They're going to be positive with respect to the cathode. The electrons are going to be released every time a diode is struck. And so for every 1 photon, you're going to get 10 to the 6 electrons that actually come out of here. Okay. Photodiodes. Remember the diodes from semiconductors? This is that for photons. Okay. So very compact, inexpensive, low power consumption, photodetectors. Light's going to strike the semiconductor, it'll generate electrical current. Photodiodes, they are a lot less sensitive than photo multiplier tubes that we looked at before. Right up here. They're commonly used in high light intensity applications, such as measuring absorbance. The more intensity that you can put out, the better they are going to work. They're built from semiconductors. These are some of the most common materials that you would use for these photodiodes. Note that we have not included the dopants, which are small amounts of atoms you would add to modulate the behaviors. So they would detect specific frequencies and do specific tasks. But these are the most common materials you would see in these, and these would be like your base that you would then add specific atoms to modify. This is actually what it looks like. So we're going to have a p-type silicon, and then we'll have an n-type silicon. These will be joined together, and so we'll create a p-n junction diode right here. And so what you'll have here is you'll have these little protective layer here, and then you're going to have your depletion layer right here. That's a little cutout. There's going to be an anti-reflective coating that you're going to have on this so that it does not reflect the light back out and then cause it to trigger itself again. The light will then come in. Note if it comes in at the wrong angles, it's very likely to get blocked and not give you the proper detection. So it's only a very set width of angles that will work with this. This is actually what it looks like, though this is a kind of old one. Mostly they just look like processors-ish now. They don't look that different. But this is a wider one. It's not that old. This one I'm seeing. So the light hits your p-type silicon conductor. It's then going to cause the depletion layer to give off signal. This is going to go to the heavily doped Si layer. Depending on that PN junction, that's going to select whether that light actually triggers this or if it doesn't. So if the light is too small of a wavelength or too low energy to cause a transition from that PN junction, then it's not going to trigger this. Okay. So the light's going to strike the semiconductor right here. Again, this is that p-type silicon right here. It's the green one. And the free electrons and holes are going to be created. They're going to give you regions of opposite charge. Because you have regions of opposite charge, that's going to give you a voltage, right? And that's going to then cause an electrical current to travel. And so when light's not hitting this, you won't have voltage, you won't have an electrical current traveling. When light strikes this, it's going to cause an electrical current to travel. Okay. This right here is that band gap. This is where this doped N-type silicon conductor comes in. By doping this in very specific ways, you can actually change this band gap right here. Okay. You can either make it smaller or larger. And so, if the energy of that photon is greater than the band gap, that's where you're going to get the electrons migrating, and you're going to get that difference in electron and hole. You guys remember what holes are, right? Holes are where electrons have abandoned. So they're places, they're energy levels that could fill in with electrons. So you've boosted the electrons up to the higher energy level, and that's going to cause a conduction. Now remember, your valence band is then going to be absent an electron, right? And it's going to want to fill back in. Okay. And so what you'll end up getting is a voltage that's across these. And typically you have a wire connected to this. And so the electricity is going to go from this back onto here. Okay. And you'll conduct that electrical, you'll detect that electrical flow, that being the current. Okay. Does that make sense so far? Okay. In case you're wondering, guess where the first place these were first used in? UV. Yeah. Fairly high energy. Silicon semiconductors respond to UV. They also can respond to near infrared. And so that's why you'll see a lot of UV, like low energy UV through to near infrared instruments, and they're very cheap. So, like, if you notice our instruments, we have our UV, vis, and technically they actually go into the near infrared. If you guys looked at the frequencies you can do, you may have noticed that it was a little bit below red. You guys ever use the verniers? Yeah. Did you ever take like a full spectrum? So what you would have seen if you took a full spectrum is it looks like this. And then you have like, like that. Okay. And what you would have seen is that it has no color here, that has the different colors here, going from violet down to red. And then it has the no color again. And the reason it has no colors on both ends is because you can't see in the very small amount of UV it can detect and the very small fraction of near infrared that it can detect. And so it has a little bit of UV and a little bit of near infrared it can detect. And it doesn't color those regions. And instruments that do that don't color those regions because you don't see color in that region. Okay? In case you ever wonder. So that's what's happening there. Now, those are the silicon semiconductors. That's usually the most cheap ones. They, not to say that they're cheap, they're actually can be very expensive and very high quality. But yeah. Now the INGAAS and lead sulfide, some photodiodes, those do respond further into the near infrared. And that's why you see instruments that are either focused more on detecting UV, or you see instruments that are more focused on detecting the near infrared. Okay. If you ever start shopping around for these because you need to get like a flow line detector, you'll see that you have to order one or the other, and it'll be like focused on this end, or it'll be focused over on this end. A little bit visible in the infrared. Okay. Now, I've already indicated this. This is a photodiode array. I've kind of mentioned it a few times now because I wanted you to start making connections. Again, it's just going to be an array of semiconductor diodes, and then you can detect the different frequencies of light using those. It can contain tens of thousands of individual photodiodes. You can use it to either get an image of specific lights, you can get different frequencies of lights that would detect. In your phone, they do both. So it both gets the full image, right, with the spatial distribution, but it also has a set of all three colors that you would use for seeing that correspond to the colors that you would see with, right? And so it actually does both. Like it has little sets of the three different colors that it's detecting to see. Actually, modern phones don't just do three colors sometimes. Sometimes they'll also do like near infrared and infrared so that they can detect better the shape, even in low light conditions. But they can get quite surprisingly, like the camera in this phone here is actually incredibly advanced. And so is likely yours. Notice they have three different detectors on modern phones. So each diode's PN junction is going to act as capacitor. It's going to charge is going to be stored on either side of that depletion region. At the beginning of a measurement cycle, each diode is going to be fully charged. When a UV or visible light strikes the semiconductor, the capacitor is going to be partially discharged. And then you'll have more radiation that strikes each diode. Less charge remains at the end of the measurement. The longer the ray is irradiated, the more each capacitor is then discharged. And this is actually why you can only go so long when you're taking like a photo or you're taking when you're doing a spectra with one of these. You cannot go past that capacitance. Once you deplete, you won't longer get any detection. Again, you'll discharge as you go along. The state of each capacitor is going to be determined by at the end of the cycle by measuring the current needed to recharge the capacitor. And so we haven't done the infrared instrument together yet, have we? Okay. We'll definitely need to make a point of actually showing you how that works and talking about it this lab period. That's coming up. So you'll notice in that instrument, you take scans and you actually count the number of scans. And so it's like 1 scan, 2 scan, 3 scan, etc. Okay. And what's happening is that you're getting a very similar effect. This is how almost all spectroscopy works. And so you get peaks, right? And then background noise, which is just random fluctuations. Okay. So if you only do this with one detection, what you'll get is a lot of noise and very small intensity peaks versus that noise, right? Is that making sense? Yeah. Because your random events are, almost proportional to your spectroscopy events, right? The difference in the number of those is fairly small. And so what happens is you take more and more of those, and what will happen is the noise is going to go down because that's random, right? Sometimes you get positive, sometimes you get negative. It's random. And so they'll subtract each other, okay? Whereas the events that matter, which are your peaks, they're not random. They're systematic, aren't they? And so they'll actually add to each other, okay? And so eventually, if you do this long enough, you're going to get consistent peaks, and your noise levels is going to go so far down that it almost looks flat, okay? Like it's not anything. And that's what's happening in these. It's doing that without actually showing you the results each time. Technically, it could show you the results every time, but it would take a lot longer, and you wouldn't have nice, fast photos that you could do. Or in this case, nice, fast spectra that you could do. Okay? So it's getting the same effect, but it's doing it without actually like processing the information in between. Is that making sense? Okay. I guess we're out of time, aren't we? Are we out of time? No, we have 15 more minutes. I don't know why I'm... God. My 8 o'clock class is just killing me. I am definitely not a morning person. Okay, so this is how this all kind of comes together here. You'll recognize this right here so far. We have our light source, right? And then we have our elliptical mirror, and then we have it going into our sample. Now, in these instruments, you can actually simplify a lot of this stuff. Like, you don't really need to select for your light coming into your sample, do you? You can actually just pass all the light through. Because in a photo diode array detector, you can actually take it through the slit. You still need to focus it into a nice narrow beam because you're still going to use something like usually a grating for this, okay? And then you're going to put it on the mirror, and you're going to get your incident angle. Now, what you're going to do, instead of selecting with the mirror or the grating, where you're moving this grating or mirror and doing one at a time, you instead have this photodiode array detector here. And so you just trigger it on all of them. And depending on which one it's hitting, that's going to be your different frequencies that are being selected for by your grating, right? Can you guys see that okay? All right. And so depending on which multiple of the wavelength you are, that's going to give you the different wavelengths that are detected by each of these detectors here. Now, note that again, this is one of the reasons why you have to run backgrounds, by the way, is that the amount this photodiode array detector actually detects each of those wavelengths may actually be a little bit different. Okay. So their intensities may, just through the instrument's detector, have a different intensity. Is that making sense? And that's why, if you remember, your transmittance and absorbances are always divided by the incident intensity that you detected on your detector with nothing there, right? Um, anybody have any questions there? Now, I haven't talked about one huge advantage here. What's a just massive advantage of this? Yeah, we've cut down on a lot of parts, and we've cut down on, even more importantly, moving parts. And so, like these, detector system like this, you could make this where this sample right here is literally something you just put in between a gap, or you just press it against and it bounces the light back instead. And this thing could be so tough that you could literally drive a tank over it. Okay. Which is actually used in military operations, and they do. They have actually driven a tank over one by accident. And the advertising people for them were very happy that it didn't break, and they got to go, you can drive a tank over this. Oh, they also had it drop from a 30-story building and still work afterwards. So you can make these incredibly tough. What's the other advantage you might be able to think of? If I have to move that grading and select individual wavelengths, how fast can I do these? Yeah, not fast at all, right? If I have to move the grading. This, I could do this incredibly fast, right? Depending on how intense I want my signals, like I could do this technically one time and it would measure in like micro and nanosecond regions. It'd be that fast, basically the speed of electricity, right? Yeah. So, um, there are massive advantages to this. Can you think of any disadvantages to it? Uh, interestingly enough, not really. Um, because this part can all by the manufacturer put in place, and then they can test it. Uh, because they can make these basically rigid boxes that you can't get into at all, and it has no moving parts, so you really can't do anything to it. These things are actually reduced gross error, operator error to nearly nothing. Yeah. This is why the instruments we give you, the first instrument you get for spectroscopy, is this type of instrument. It's that Vernier visible light spectrometer that you typically would use in like first or second semester general chemistry. And they're just incredibly reliable, very, very difficult to mess up. Um, yeah, because the design is so simple. No, the biggest disadvantage to this is that like you can make these gratings and mirrors huge, right? So if you give yourself enough space, notice the infrared spectrometer is quite big, isn't it? Okay. If you give yourself enough space with these instruments, you can actually get very, very fine detections, very, very small wavelength ranges that you can detect, right? In this one, you're kind of limited by the photodiode array detector, right? And so, really, you're kind of limited on the size of how good of a semiconductor you can make, which is not usually going to be as good as like an FTIR can manage, or a very large grading array and a very like large instrument could match. Interestingly enough, the instruments haven't really gotten that much better in terms of like resolution of wavelengths since about the 1950s ish, 1960s ish, somewhere in there. And that's because they used to just. This is kind of like crazy to think about, but they used to basically just make thousands of gratings and then use these huge gratings, like table size gratings, and then like test them. And then the one that worked, they took. So, like, very high end instruments would be the size of a room, like this room, and they'd have these massive gratings, very, very dense gratings that they may have made thousands or even tens of thousands of gratings before they got the right one. And then they used the rejected ones for other instruments. So you can kind of brute force your way to really nice instruments if you're willing to. My advisor had one from the 1960s that was same resolution as the brand new like $50,000 instruments, and it was a $100,000 one from the 1960s, which with inflation would have been millions of dollars instrument. Yeah, who was actually given that one? Okay, we came up with all the things on our own, didn't we? Yeah. Now the other thing to keep in mind with this is noise is more of a problem with these usually. So you don't really have a lot of process in here that prevents stray light. Can you kind of see that? In the previous process, it had to match up exactly with the angles to go through the system, right? And so stray light would have been pretty unusual. Stray light in this is going to be much, much more common, right? Because there's a lot more angles that you can approach that. This right here is a charged coupled device. That's a CCD. These are very sensitive detectors. They'll store photo-generated charge in a two-dimensional array. And again, we have kind of a similar setup, but a little bit different because it's going to be a two-dimensional array. And so what we'll get here is we'll have an insulator, and then we'll have a silicon electrode. We apply a voltage to this. The electrons are then going to be stored beneath the positive electrode. And so what we'll have is a set of electron and electron hole. Whenever light strikes this, okay, then we're going to have it where the electron that was in the hole is going to be boosted up into a higher energy state. Now, the higher energy state is actually being created by our voltage here. And so we'll actually have it boosted up into this higher energy population right there. And that's going to give you your hole. The hole is going to be, did we talk about holes migrating? Or do you guys remember that at all? Okay. So what happens in these semiconductors is, remember, they're atoms, right? Okay. And so if you create a positive charge one place, then the electrons near it can get moved over, and then your hole, which is your positive charge, will migrate over. Does that make sense? Yeah. It's not super complicated, but it is kind of a weird terminology, right? Because you don't think of the positive charge, which is lack of an electron, as migrating. Okay. Yeah, so that's the hole migrating. It migrates right here to the N-doped silicon substrate. Again, this is going to create a voltage differential between the P and N-doped substrates. And so you will get a voltage that will develop, and you will get a electrical current that will then change. Okay? And so you can then detect that electrical current. And that's going to store there and beneath that positive portion. Now, each electrode can actually store 10 to the 5th electrons approximately. And so you can get a buildup of approximately 10 to the fifth, depending on this light hitting it over and over. That's your sort of capacitance that you're going to have for this. Okay. Okay. Now, there's actually kind of a cool thing here. You can modulate this behavior somewhat by changing this voltage slightly. By the way, do you guys know what sort of voltages you would typically see for like a USB? It'd typically be between 5 and 12 volts. Yeah. So this is going to be a pixelation right here. So here we have these columns and rows, and what we're going to have is light hitting this over the time is exposed. Do you guys know what exposure is? You ever heard of that term? It's in terms of like photos. Yeah. So this is why, like, if you take photos in the dark, things get blurrier, right? And it's because your camera is exposing this longer so that more light can hit this array. Is that making sense? Okay. And you'll see that colors get a little bit washed out from that too, and can kind of flicker in and out a little bit. Okay. So pixel is going to be an element of a picture. And when we have these arrays, what we need to do is we actually need to read these and write these, by the way. This is the same way a screen works, in case you're wondering, on your computer or your TVs. So we actually need to read these very carefully so we can read one after another, right? And because they're so densely packed, like there's not a way for your electronic to go like out of space and just read one. Okay. And so what it's going to do is it's actually going to do what's called a serial shift collection. And so what you'll have is you're going to have this serial array right here of these different pixels, which are those individual detectors. And it's going to essentially move these off serially, one after another. Okay. And it's going to detect that voltage. Now, typically these voltages would be very, very small. And so you typically have a multiplication stage in this that is going to act kind of like an amp. Do you guys know what an amp is? For like stereos? Have you guys ever plugged your phone directly into like a speaker? No? Bluetooth only? You ever had a kind of crappy speaker that's like really small and it doesn't have its own volume controls? It just does the volume with your phone? Okay. That is what happens when you don't have a multiplication stage. And then you ever had a speaker and your Bluetooth is hooked up? Your volume on your phone is really low, but the volume on the speaker is very high. And it does like these crackling pops. No? Try it out with your Bluetooth speaker if you have separate controls for the two, where you can control the volume on your phone and the speaker separately. And you'll see what I'm talking about. Like you'll get a lot of noise because the speaker is multiplying whatever's coming in. Okay. We'll call that a day. Do you guys have any questions at all? No? Okay, please do talk to me if you have questions. Because I really would like you guys not to need to do a review thing after the exam. Can you guys get to the review and it's all working? Yeah. Okay. We're going to call that a day.